Okay, can anyone confirm that?
Yes, your screen is visible.
Yeah, okay. Is the presentation?
Yeah, it is.
Okay, and this, I can see one window, small window. So can I like how to?
You can go in presentation mode. You can just present if you want.
No, this is fine. So this I think this window is fine. So I am presenting from open board so that I can write equations or figures if I want. But actually, what I'm seeing is okay. This can you see this one? Like there is a small WebEx like
That
window.
that WebEx control panel should be at the top of your screen, and if you
Okay.
click on anywhere on your presentation, it will vanish. So you need to.
No, actually, it's not going.
Where is it? I cannot see it. So
Yeah, I understand then. Okay, so then let it be here. Okay. So if from the other end it is not visible, then I think it's fine. I think, yeah, it's just minimized. Yeah, I think this is nice. Okay, so we'll go ahead then. And let me even remove this. Okay, so now I think my presentation is properly visible. So good morning, everyone. Today I'll give my presentation in this topic, optimal design of thin walled plate and cell structures for maximizing its buckling strength. And why I have chosen this problem, if you see, thin plates and cell structures are widely used in aerospace and mechanical, even naval structures. So this like if the structure is thin, so then due to this small thickness, these structures are kind of susceptible to buckling failure. Okay, so because like if you remember when you play with some long stick, then if you try to give a compressive load, then if the stick is actually longer, then it is a tendency, its tendency to have a buckling mode, like out of plane deformation, it will happen. Okay, so and if the streak is the cross section is uh, high, or it is like not very thin, then you cannot actually have that buckling mode of failure. So we call it is a failure because when it goes that kind of unstable mode, then it cannot actually take a certain loading. So the purpose of that structure is to take certain load, and that purpose will not be like fulfilled if it goes to that kind of unstable region. So we call that's why buckling is kind of a failure. So there are actually different failure mechanisms of structure. Like it can fail in a kind of fracture mode, and also it can, like when you have dynamic loading, then it can have resonance and all. Then there can be different failure mode. But buckling is due to static loading, so there is no time invariant load. The load is maybe very slowly increased, so you can say quasi-static loading. And then due to that higher load, it is going to the unstable region, which we call buckling. And this buckling phenomena occurs mainly like if it is one-dimensional structure, then a long column. And if it is two-dimensional structures, then plates and cells, where the thickness of the plates and cells is relatively smaller. Okay. So, and we find this kind of structures in mainly aerospace and mechanical and naval architecture, because in these engineering fields, the weight is important criteria. So you have to have a lesser or like weight sensitive structure to save fuel and etc. So, so that's why we use thinner structure, but we have to have sufficient strength for those structures. And the complicacy also, like it becomes more complicated if you have a different cutout and stiffeners added to the structures, because like you have to have cutout because of so many reasons, like you want to remove some weight at certain locations. So then you just reduce by like inserting different holes, and you try to like remove material where the stresses are less. So you have to choose proper locations. And also we use stiffeners to increase, like to give different strength in different transverse deflection. Like it gives stiffness to bending. So mainly it actually like the stiffeners are used to give that's the name suggests that it is given for stiffening the structure. Means it gives some rigidity. Okay, so these like these cutouts and stiffeners, if you add, then the structures becomes complicated, and you may not have actually closed form solutions for these structures. So so then the only way you can solve these problems by computational methods such as finite element and so like related numerical techniques. Okay, so then if we approach this kind of problems when there are plates and cells with cutouts and stiffeners, and we want to optimize those like design parameter of those structures, then we have to choose this route of having numerical analysis, and then in that we can try to solve or try to optimize this problem. So here I'll just take few smaller problems, not kind of exact structure which is used in aerospace structure. So we'll start with one or two case studies where we'll approach from academic interest. So we'll take few smaller problems, and then we try to see how we can set up these problems and try to optimize a few of these like plate or cell parameters. Okay, and we'll also see by changing different parameters how this optimal design is actually changing. Okay, so the first problem, let us take this plate which is of rectangular shape, and there is one single cutout which is, let us say, a circular shape. Okay, so rectangular plate with a circular cutout, and that cutout can be anywhere in this plate. So we were interested to know which position of this cutout is actually the optimal position which can give you the maximum buckling. Okay, so this problem is, though it looks very like a simple problem, but analytical or closed form solution for this kind of problem is not available. So if you have unperforated structure, like there is a rectangular plate without any cutout, then we have analytical solutions, and we can approach this problem like analytically using your like some symbolic packages like Mathematica, Maple, and all you can use. and you can actually solve this problem. So there will be some differential equation, and that differential equation you have to solve. You will get some closed form solution, and if you use symbolic package, then you can get that closed form solution using algebraic form, and then you can see which parameter actually is influencing that final output. Okay. But here, the presence of this single cutout itself is a kind of analytical solution. A simple analytical solution may not be available. You can have some series solutions, etc. Then that itself will become very complicated. But it is like if we use finite element approach, it will be very easy to handle this problem. Then, like if we want to optimize this structure, then we have to somehow link this finite element solution to some optimization scheme. Okay, so this will have like two softwares here, one for the finite element analysis and another software I'll use for the optimization study. So Ansys has been used for finite element study, and then I will actually club optimization scheme which is available in Matlab to this finite element simulation in Ansys. It's kind of a co-simulation. They will talk to each other, and then I'll try to optimize the location of this cutout within this rectangular plate. So there are studies available where the systematic this optimization is not done. What they do, because you can see you can choose this like n number of locations within the structure, and then you can do some design of experiment kind of study, DOE. So you just choose certain locations, and then you see which location is better. So that may not be a true optimum. So unless you approach this problem by certain standard optimization technique, so you may not get the true optimum. Is there any question? Okay, may not be. All right, so here I will first do some validation study. So as I told, we have used Ansys for the finite element analysis. So first we need to find whether Ansys is kind of capable of solving this problem or not. So first we have carried out some analysis of unperforated plate, so without cutout. So that has a solution available in some books, analytical solution. You can see that the Ansys result and the analytical solution, they matches very well. And then there is one like case we have taken where circular cutout is taken, and there were some literature values and solutions available in the published work. So that comparisons also that they're also in good agreement. So here we are choosing to represent our buckling load as a normalized buckling load, and the normalization is done with respect to the buckling load of the unperforated plate. So for unperforated plate means there is no cutout, then you have an analytical solution, and that is the analytical solution for that. So this is the final output, and there is some K value. K depends on like, the boundary conditions, etc. So here we are using what is called simply supported boundary condition. So all edges simply supported. So simply supported, I think because in beams we get simply supported boundary condition. Basically, simply supported boundary condition means you have displacement restricted, but rotations are allowed. Okay. So here, this like you can take this analogy, like this formula, to analogous formula of the beam or column buckling. So you know that for Euler column buckling formula for simply supported column, more than simply supported, it is pi square EI by L square. So similar to that, you can think that for like a unperforated plate, you have certain formulas. So we are using that load to normalize this like buckling load, whatever we are getting for the actual case. So this N0 critical is the load, buckling load for the perforated plate, means the plate with cutout. Okay. So NBF will try to, because this number for a given plate geometry will be constant. So because we are not varying anything else, so this will be constant. Then you take some circular cutout and then you change different locations. This N0 critical will actually change because of this placement of the cutout at different location. And that way NVF will also vary. So we try to see which is the location that gives the maximum NVF. Okay, so before going to do actual optimization study, so whether it is a true like optimization problem or not, so to understand that, what we have done, we have actually to see what is the effect of the cutout position, we have taken a rectangular plate, and then as we do using DOI study, so we have like made some grids, and in each grid points, we have placed the center of the cutout, and then we have found what is the NBF. So this is done all through the plate. And then if we plot these numbers as a surface, so the NBF at different locations, locations means the cutout of the center of the cutout is placed at different locations within the plate. And then corresponding the NBF, if we plot as a surface, then this surface, the surface is shown here, will be the output. So here you can see AR is equal to 1 means when you take AR is aspect ratio, which is defined by A by B, where A is the, this is B and this is A. A is the length and your B is the height. So when you have aspect ratio on square plate, the surface plot looks like this. So that shows that the maximum buckling load can be obtained when the cutout is placed towards this edge, these two edges. Whereas when we have aspect ratio 2, then we can see the surface plot shows that the maximum is like the optimal location is towards the center of the plate. When you have aspect ratio 3, then there are actually, because this is symmetric, the loading is symmetric about the X and Y axis. If you take X and Y at the middle, so that's why you can see if I put here or here, it actually doesn't have any influence. So they are same basically. So that's why everywhere it is symmetric about this line, as well as it will be symmetric about this line. So these surfaces have two symmetry. Okay, so then if we take only 1/2 or 1/4, it will be fine. So we can choose for optimization, we can have the positions only within this first quarter of the rectangular plate. So we can vary the location of the cutout within this first quarter. And we can see for aspect ratio 3 that somewhere in this line, so between 0 to the center to the right edge, there is some optimal location. Whereas for air aspect ratio 1.45, you can see there can be like a transition. So here this is also some at the center also the buckling load is higher, and also at the edge also you can see the buckling load will be higher. So basically if you see if you start from 1 and then increase, so at 1 the maximum was somewhere here, and then as we increase, this surface is changing, like this middle one is going up, this portion actually is moving up, and this is going down. And then at certain transition aspect, so this may be a transition aspect ratio where almost like they are same, and then after that if you further increase, then this will go up and this will down, and you may get at aspect ratio 2, it will be something like this. So basically there are actually you can see the surface plots are not same for different aspect ratio. So it is very difficult to kind of have a guess of what can be your optimal location. It depends on so many things. And this actually is done for only kind of plate with isotropic material properties. So isotropic means the properties are same in all the directions. And in aerospace structures, you can see mostly nowadays we use composite. And composite has even like a complicated response. It has different properties in different directions. So then that will lead even further complicated scenarios. So that means like a intuitive guess of where can be the maximum, where can be the optimal location of the cutout is not possible. So we have to like go with formal optimization scheme or optimization technique to arrive at that. So that is the like motivation, and then we'll set up this problem. Here, this is our optimization routine. So here you can see, as I told, I am using two softwares. One is Ansys for FEM, and then you have Matlab code here. And we like Ansys actually give you this. You can see, let us say this is my parameter. So here the parameter is the center location. So I am just defining with two parameters, XC and YC, which are the center locations. And for each parameter, I can get one n critical, which is the buckling load. And then Matlab, like it is set in this Matlab, either you can use some optimization scheme like a gradient-based optimization scheme like FInsearch, or genetic algorithm, or so many other techniques available. So you can use the inbuilt optimization techniques available in Matlab. And then you just feed, you first choose a parameter and then feed it to Ansys. And Ansys will solve for you what is the n critical, and it will give back this value. So it's kind of a scalar optimization. So that then use like from this n critical, because we want to maximize this n critical. So and every optimization scheme in Matlab actually is a minimization problem. So you have to just modify this like objective function a little bit. So let us say n star critical is that objective function. So you want to minimize it. And then Matlab will feed this n star critical to the optimization scheme, whether it is GA or M And then based on the algorithm, it will feed you the next iterative value. and then it will again, Matlab will give or send that information to Ansys, and Ansys again will give you the new number and critical, and then it will be like this iteration will go on till you get the kind of a converse or like your until you have the optimization result obtained, it can go on with the, like this iteration. Okay, so here you can see for this problem, the objective function, as I was telling, can be defined using this way. So this N0 critical is a positive number because buckling load is always positive. So it's a positive scalar value. So you get a positive number always from Ansys. And then just to simply, because you want to minimize it, so you take a negative of that number. So you want to minimize the negative of that positive value which is obtained from Ansys. And then this thing is done to incorporate the constraint we want to impose. So here the constraint is like, if you see the center location, because there is a dimension of cutout. So that cutout cannot, like the center location, because if you see this is your diameter of the cutout, then the center has like, it will, from the edge at least like d distance away you have to take. So sorry, this is the center. So this distance has to be d by 2. So this has to be d by 2. So at least it has to have d by 2 distance from the center, sorry, the edge. And then even you have to give certain more margin, because in Ansys, if you just keep this two same, then there is actually some modeling issues in this location, because you have zero length of elements, etc. Then you have meshing difficulties, and you will not find any edge here to give your boundary conditions. So to avoid these situations, we just take little more. So your maybe like you have the range of that center value xc start from 0, and then it stops at little like the gap. This gap is little more than d by 2. So this is your the range of xc you should play with. Okay, so this, let us say this is your xcr, this is the range. And similarly, you have the same thing for ycr. So you have two ranges of xc and yc. And then you don't want to like go beyond these ranges. So that constraint you can impose simply using this logical variable. So this is actually a logical variable which is used in Matlab. When this logical variable actually is true, then Matlab will produce value of 1. And when it is not true, then it will be giving you 0. So basically, if you see that when xc is more than xcr, so you want to discard that case. So to discard that case, what we are doing, we are using this logical variable, then it will give you 1. And then you have a very large number. So basically, you are adding a very large number to some negative value. That means it is going to the positive side. So then your optimization algorithm will kind of not take that particular case, because it has very higher, because you are minimizing, and that value is a large positive number. Okay, so this way we can actually, it will think that there is a big wall, it will actually come away from that wall. So that way we can have some penalty added to this objective function, to discard these XC and YC values, which is going beyond XCR and YCR. So this kind of trick works in Matlab, and we have seen that we are getting a solution within the prescribed range. Okay, and this is the output we have got for different aspect ratios. As I was mentioning, that the optimal location is dependent on aspect ratio of the plate. So if you see when like aspect ratio is increasing, we are increasing from some smaller number, maybe it is 0.5 or 0.6. So you are starting with kind of a plate where the height is more than the length. So this is A and this is B. So then aspect ratio is less than 1. And then you have a square plate where aspect ratio is 1, and then you have rectangular plate like this. So we are starting with this, and then you can see when you have this aspect ratio smaller, then the optimal location, these locations are near to the edge. You can see it is exactly like at the range where it is given. So it is near to this edge. And then when aspect ratio actually is, I was telling that there is a transition. So it moves from edge to the center location, and that happens around 1.5. So then it becomes like maximum location is here. And then it goes, and then again it is increasing, and it is increasing with a nice curve. You can see as we are increasing the aspect ratio. And YC value, so it is this was obvious from our surface plot as well as this optimized result, that YC value is 0 always. The optimum, so optimum location is always in this line. Okay, so in this y equal to 0 line, these optimum locations are obtained. And then this plot actually to convince ourselves that these optimum locations are really optimum values or not. So we have just taken some arbitrary locations like center location, and then XCYC is A by 4 by 0. So basically it is somewhere here. So this location. So you put the aspect ratio for all aspect ratio, you put this that circular cut put at this particular location, and you see what is the buckling value. And then you put at center, and you see what is the buckling value. And then you put at the optimum location which we have obtained through this optimization scheme. So if you compare these three locations, the NBF, then you will see this NBF, like for optimum location, it is giving this curve. So this is what the optimal or maximum buckling load we are obtaining from this optimization scheme. So you can see that this at least like partially it shows that it is the true optimum. Okay. And I was telling that the optimal location actually is very difficult to guess a priori. So you can see like somewhere, sometimes we say that because this is the mode shape. Mode shape means when we have we are going to that buckling stability, how the outer plane deformation will look like. So basically this is like it is loaded in this direction, the plate, and when it buckles, then this goes down and this goes up. So there is actually some sine, like half sine waves you can see in this particular case. So there are two half sine waves in this direction, like it is going this way and this way like that. And it is one half sine wave in this direction. So basically, it is somehow like this is the mode shape for the first buckling mode. And you can see here, this is the optimum location, and optimum location is sitting at the nodal line. Nodal line means the line where there is no deformation in the buckle, like when it is buckling. So some lines will have no deformation. So this line, there is no deformation. So in this case, we can see the optimal location we are getting in the nodal lines. But if you see for the second case, when we have taken AR is equal to 2.5, then the nodal line is somewhere here. And then the optimal location is even where there is a maximum displacement occurring. So this is going up, this is going down, and this is actually at the maximum displacement. So whereas here in this 3.0 case, it is actually again near the nodal lines. So then we cannot conclude that it will be always in the nodal lines. So it can like be anywhere within this rectangular plate. So that justifies that we need to have the optimization scheme adopted for getting this optimal location. This is another way we can show the optimal locations. So aspect ratios varies, and then you can see it was here at the edges, then moving to center, then going away from the center, but it is not going in a very uniform way. Sometimes it is near to the center, sometimes it is near to the edges. So that way you will get some curve, which we have seen earlier. And then this is like how it can vary. These optimal locations are varying with different cutout size. And this is for different plate thickness. You can see cutout size has certain influence on the optimal locations. You can see this is changing here, and there is also some changes in these locations. But thickness have very minimal effect. So if we change the plate thickness, probably the locations of the optimal locations of this circular cutout will not change. Okay. And now, so far what I have mentioned that you have a circular cutout, but you see it is not always kind of necessary that the cutout shape will be circular. So in many cases we have seen there are different cutout shapes, and one shape can be kind of elliptical cutout, and there are some other shapes. So these are actually like we want to do some academic study, so we'll not go to like the actual shape, which maybe the parameterization will be difficult. So what we have done, we have taken some elliptical shape, okay, and in the elliptical shape there will be then 3 parameters. So we can see for circular cutout only XC and YC we have changed because we want to keep the area of the cutout same. So that's why the shape of the or the diameter of the cutout earlier cases it was not varying. So here also we'll keep the same cutout area, and we'll then change the location as well as the orientation of the cutout. So here orientation will also be one parameter. So this optimization is done using T parameter, and here we have used again GA for the optimization. And then we can see like if we have such elliptical cutouts, then the optimal theta will be close to 90 degrees. You can see this line is almost near to the 90 degree line. Okay, so it is this position which will give you the maximum buckling load. So not this position. Okay. So this is the optimal location, optimal placement of the cutout for getting maximum buckling load. So this is one observation, and then optimal locations XC, YC also you can see there are actually certain changes compared to the earlier case. There was like it is going like it is here it is remaining at the center, XC is equal to 0, and then going away from the center, and again it is coming back to the center at certain positions. Okay, and then again it is going back. So this is like done using the changing the aspect ratio A by B. Okay, so you can see now that for different cases, like we have changed the cutout shape from circular to elliptical, but then we are getting so many different behavior. Okay, so the XCX, XCYC changing, there is an optimal angle also we are getting. And here, this plot actually showing again to like if we choose a certain predefined position of the cutout, then whatever buckling. Is there any question?
Our diagram is to be on blank side, preferably. Opposite to theory. That will be better.
Yogesh, are you speaking? You have a question?
No, sorry.
Okay. All right. So now we just this is the surface plot again to see how the surfaces. If we again use some grid points to see how the position of the cutout, if we change it within the rectangular plate itself, then how the surface will look like. So here also you can see there are certain maximum positions at different location within the cutout. And here we have obtained, because there are actually 3 parameters, but we cannot like have a surface by changing 3 parameters. So one parameter we have fixed. So this is your theta equal to 90 degree. So the cutout is placed in the vertical position. And then if we vary the cutout at different position within the plate, then we can obtain what is the maximum buckling load. The corresponding buckling load, and then we'll see how the plots look like, and then we can have some idea of where the maximum buckling load would be. So here you can see this is the place, here this is the place. So to see like whether some intuitive idea we can get by changing the aspect ratio. And you can see that really these surfaces are not very similar. So they're different for different cases. All right, so now I was telling that we can have orthotropic plates. So here orthotropic means your material properties are different in different directions. So you can see if I take some typical orthotropic material, then it can have 130 GPa in one direction, 10 GPa in other direction. So there is, like you can see, around 13 times different, the Young's modulus. So that also can influence the position of the cutout. So you can have also different laminate sequence. If you have idea about composite, you can like understand this. So there are different like layers we can stack, and then we can build some laminate. So if we just take one certain case, then how your optimal locations will be different. So we just wanted to see that effect. So material orthotropy is considered here. So before going to optimization study, we have validated with the literature values, and these are some validation study. You can see they are matching well, so we can go ahead with this optimization. And this is where the optimization results we have obtained. So this is your XC, YC, and this is your optimal theta. So again, here we have used elliptical cutoff. So now the main point here is you can see for isotropic case, the optimal theta was 90 degree. But here you can see it is varying from like close to 120 degree to some 45 degree. And when we have aspect ratio changing from 1 to 5, this actually changes. So it is not remaining same. So optimal theta changes, and then optimal your XC, YC also changes. YC very close to 0, but some places it is not 0. And XC, it is also very close to 0 at certain aspect ratio, but for other aspect ratio, it is far away from the center. So the point is, like, you can see there are influence from the shape of the cutout. There are influence from the material parameters, like if it is orthotropic, you will have different behavior. If it is isotropic, you will have different behavior. So this justifies, like, if we really want to get what is the max, like the optimal position for a given plate, then the only way we can get that by adopting certain optimization scheme. And this AFM and Matlab is can be one combination, because for this kind of problems, you may not get analytical solutions very quickly, or if you get may not be, like, it may not be tractable. You may have so many complicated equations to handle. So better we can go with AFM solutions, and then we can set up this optimization scheme using some co-simulation technique. Okay. And so these are some summary which I have already mentioned, that it has like material orthotropy has influence, aspect ratio has influence on that. So you have to adopt a systematic approach of optimization scheme. Okay. So now I'll just take one. So this is my second problem. So I have one more, but this is a little different problem. Maybe like we have seen certain geometry in different engineering applications, but I was just trying to see if I try to optimize the shape of the cross section of certain column. So basically, this is open cross section column, which like you have I section, T sections, etc. They are called open sections, whereas your circular section and rectangular cross sections are they are called as closed sections. So in many engineering application, we have these open sections columns, especially in aerospace structure we have. So if I try to optimize the shape of the cross section, which can give the maximum buckling strength. So again, that problem is not easy because the buckling of certain cross section will be having both flexural and torsional mode. So let us say what I want to mention. You can see if I go to the next slide. So here you can see how it is. So this is a typical cross section. So this cross section we are taking for the validation study first, and then we'll see what is our parameterization. So here this shape, if we try to see what is the buckling mode, then we can see there is actually a flexural mode like this, and also this like cross sections, you can see somewhere this was here, then here this has become like this. So basically there is a twist happening. So the cross section is rotating like if you move along the length, and the mean position of that cross section also is like having some flexural mode. So this is called flexural torsional buckling. And again, analytical prediction of this is very difficult. You have like coupled differential equations, and I can show you like what can be, yeah. So here you can see there are some, so this is one for particular, like one simple case like this. You have this many equations. And then, okay, this is not appearing. It was like having maybe some parameter and then equal to 0. But the point is you have certain B1, B4, and these like these are actually not constant coefficient. They are actually function of these parameters, and they are very complicated functions. So like though I have analytical solution, but it may not be tractable to use them in optimization scheme. So that's why again we can use FEM approach. So for certain cases we have just seen that FEM and analytical is matching well. So but analytical will take time, and for optimization setup it may be very difficult. So we can go with Ansys and Matlab based optimization scheme. So here, this is our parameterization. So here I am taking this shape. So there are 9 parameters. So 2 are angle parameters, and others like 7 are the length parameters. So you can see this, all this 9 parameters can give you so many regular and irregular shapes. So regular shapes, we can get something like, you can see some H section you can get if I have parameters chosen in that way. So here you can see A1 is 0. So in this particular case, A3 is 0, then A4, A5 same, and then A6, A7 same, and then A8 and A9, they are 0. So that will give some H section. And then you can, so H and I, you can look at this way, then you will see that this is H, and you can look this way, then it will look like I. But for I, actually, we say that this is actually smaller. And H section generally, your wave is smaller and the flange is larger. Okay. And in I section, the wave is larger and flange length will be smaller. And there you can get T sections also from here, like for certain parameter, if you set, you can get T sections like this. You can get also C sections from here. So this is actually a typical parameterization which can give many regular sections, and as well as the irregular sections also you can get. So here we want to just keep the area of this cross section same. So let us say the thickness for each like flange element. So here you can see this is one plate element, small. So this is the cross section. So main beam is actually going like this. So this is a cross section of the beam, and then there will be like, this is the one like smaller plate element you can think for that particular beam. Okay. So the thickness of this each plate element will be same. So, and then if we keep the sum of AK, where AK is going from I to 1 to 7. So these are length parameter, and we can keep sum of them as constant. So basically the area of the cross, the total material volume, you can say, is not changing. So keep the material volume same, keeping like the length same, and then the cross section, this sum of AK is equal to some number, which is 190 mm. Then we can try to see what will be the max, like what will be the optimum parameter which can give you maximum buckling strength. Okay, so this problem can be set in that way. So we have range of this AK from each one can have maximum 190, and then the angle it can give maximum up to 180 degree, and then sum is 0. Sorry, sum is 190 mm. And then we can go for optimization as we have done earlier. And then this is, let us say, this is one cross section which is called cruciform section. And that is like the base model which we'll try to compare. Okay. And this is again, optimizations scheme are very similar to what we have done earlier. So Ansys, Matlab, and then you have GA, and then that will give you the optimal result. Okay, and this is one screenshot where GA is converging, you can see. And these are certain parameters. These are the output. Okay, so I'll give you pictorial representation of this parameter value in the next slide. But here, one thing you can just notice that this is the cruciform section result, and this is the first case. So this is your length 500 millimeter, and then 750. So length we are increasing, and we are seeing what is the cross section. So here you can see the increase is 236%. So it's huge amount of like increase in optimum, like the buckling strength. So then here 147, then 31, then here actually is 0 because the cruciform section turns out to be the optimum in this particular case. So the base model is the optimal model. And then again it is changing. Okay, so this is done for different length. So you can see as length increases, the cross section actually changes. So here, this is the optimal cross section. So here you can see this is close to eight sections, and then it is some arbitrary sections, and then it is becoming close to cruciform, and then this is exactly cruciform section. And then it is moving towards similar to some T kind of sections here. So this way you can see as length. So this is actually CS1, CS2, CS3 are for different lengths. So as length changes, the shape of the optimal cross section changes, and when it is shorter, you have 8 sections. When it is intermediate, you have cruciform sections. And when you have higher lengths, then you have T sections. So this you can get some idea about like, yeah, so this plot we have like this table. In this table, what we have done is we have taken certain C6 like standard sections by selecting parameters. You can see you have chosen parameters. These are 0 values, and there are A2, A5, A7. These are defined, and that will give you a standard C sections. So from the parameters, we can choose them judiciously to get different sections. That these are actually regular sections, and we can see like if we take regular section and then we get the buckling load P critical, and then we compare them with the P critical of the optimum solution. What is the ratio of these two? So here you can see when the length is small, then the ratio is kind of is higher for each section. So you can see when each section, then the ratio is 0.95, and then it is reducing to 0.63. So here you can see this is like in C section is 0.39, H section is 0.63, then this is 0.19, this is 0.2, and this is 0.4. So maximum we are getting here. So the bold sign is given to the maximum value. So you can see the maximum was for first two cases, it was H section. And then the middle, we got cruciform is kind of better for this middle length. And then T sections is giving the highest one. But you can see at maximum we can go up to 0.95. So, and here cruciform was the optimal, so that's why it is 1. So, and for other cases, you can see for this 750, we got the regular section can give maximum 0.63. That means the optimal location, optimal shape is not very close to this regular section. That shape is really different. Okay, so regular section is giving only 2.63. So this is one observation that H section is kind of better for lower length, for in intermediate length, cruciform is better, and then T sections will be better for higher length. And some idea of like why this is happening, we can get from here. You can see when you have longer length, it buckles in flexure mode, and shorter columns actually buckles in torsion mode. And flexure mode actually is mainly dependent on the like minimum second moment of area, because it is it can kind of Euler buckling formula will work. So I minimum is actually maximum for this T section. So that's why you have higher buckling strength for T section when you have longer column. But for shorter column, actually H section will be better, because in torsion buckling actually is a little complicated. So you have so many parameters to judge which one will be better. Okay. Yeah, so this, I think these points I have already discussed, so I can skip this. And this is the last problem, problem 3, where we have taken a cylinder. So first I have taken a plate, you can see, and then we have taken column section. And now in aerospace structure, this kind of geometry also is used. So let us say I have a cylinder, and this is subjected to both axial load and also lateral pressure load. So here we are trying to see like what is the surface profile. So this profile surface, which will give you maximum buckling strength. So to get the surface profile, outer surface profile of the cylinder, we have done like we are using symmetric profile. So the profile is symmetric about the midline. And then we are using 4 parameters here, A1, A2, A3, A4. And then we are just getting this spline curve using this parameter value. So you just generate a curve using 4 parameter. And then you reflect, you get the other half. And then you use revolution, surface of revolution to generate the whole surface, like 3-dimensional surface like this. Okay, so this is how we have modeled the surface profile of the cylinder, and here A1, A2, A3, A4 will be the parameter which can generate the surface profile. So basically, we can try to optimize this four parameter and see what can be the best surface profile which can give maximum buckling load. Okay. So again, this is actually one more thing here we have incorporated. So this exercise is done for orthotropic cell. So orthotropic materials is used. And it has been found that only increasing the buckling load will not give the ultimate kind of failure strength of the cylinder, because it happens that buckling is mainly stiffness dominated. So it depends on the Young's modulus of the materials. So for example, if you take simple column, so the buckling load of that column is pi square EI by L square. So basically it depends on the material stiffness and some geometric parameter. So material strength actually doesn't come into the picture. But it may happen that you increase the buckling strength by changing your certain profile of the cylinder and all, but it may become weak in strength criteria. So it may fail due to the material failure. So that's why you have to take both into account. You have to choose a certain shape which has higher values, higher strength in both these criteria, buckling as well as strength. So that we have tried to incorporate it in this model, in this exercise. Here you can see we are taking buckling load, and here I'm using nonlinear buckling load. And nonlinear means there are again eigenvalue buckling and nonlinear buckling. I will not go to details of that. Nonlinear buckling means you can sorry, you can because there are certain imperfections which or material, like there's some local flaws and all, which actually can influence your buckling load very significantly. So then what you have to do, you have to consider these little imperfections and all, and then we have to use a nonlinear kind of analysis to predict what is kind of the buckling load due to these certain imperfections. Okay, so this is done using nonlinear buckling load, because eigenvalue buckling is very ideal, and it may not be close to your actual practical scenario. Okay, so nonlinear buckling is done in this problem using geometric imperfection, and then we have done failure criteria using SAYU failure 3. So these are actually composite failure criteria. So we checked whether our predicted structure, like the candidate structure, whether it is failing in SAYU failure criteria or not. So if it is failing, then we have to discard that candidate design, and then we have to move forward. So that way, we have set up. So this is our, again, the modified objective function. Here we are trying to minimize this, and also we are trying to discard those design which is having failure index is greater than 1. So it should be less than 1. Okay. So sorry. So this way we can set up this problem, and then we can again do co-simulation in Ansys and then Matlab and use GA, and you set up a termination criteria. If termination criteria is satisfied, then you stop there, and otherwise you continue. Okay, so this is a way we can do iteration and finally arrive at the final output. And this is the output. Here, these are the K values. We have got K is like the AI values normalized with respect to the radius. And when it is 1, it is the AI is equal to radius. So you can see for axial compression, we got K1 is close to 1. So that means it is the perfect cylinder. So when you have only axial load, then the optimal results are the perfect cylinder. But for other cases, when you have lateral pressure only and then combined load means both lateral and axial, then you have certain configuration. And you can see this is the base model, which is the perfect cylinder. These are the buckling loads. And then this is the optimal load, which is really 6 times higher for the first case. And then this is 4% increase you can get for this case. And this is for this case, the base model itself is the optimal model. And here you can see, if we just using the buckling strength without considering the failure criteria, which is SAYU, then we can get even very higher values, like you can see 214, here it is 114. That means this buckling load, though it is like stable in like this configuration, maybe it will be giving higher buckling load, but this model will fail in strength criteria. So when you consider strength criteria, you can see the buckling load or the ultimate load is actually reducing. So that is one observation we can get. So every time if you only take buckling strength, you will get higher value of the load. But when you consider strength criteria, then that will reduce to some other value. Okay. So this is one, and then this is the shape of the surface profile. So when it is axial load, you can see this is the perfect cylinder, and for lateral pressure and combined load, it is having some surface, and we have seen that when we have combined load, then it is like the pressure, if it is some axial load is added. So you can see here, this is your only lateral pressure. Then you have axial load added, so it is flattening down. And then when you have only axial load, it is truly flat. So axial load actually flattens the optimal curve, whereas only lateral pressure, then you have a lot of like waviness. So this is for L by R equal to 2. Earlier it was L by R is equal to 1. That means the length we are varying, and we are checking how the optimal shape is changing. And here these are some three-dimensional kind of figures. You can see how this is for only lateral pressure load, this is for combined load, and this is for axial compression. Okay, and this is L by R equal to 2. So axial compression, if you add, then it try to flattens the optimal surface profile. Okay, so all right. So this is just one more exercise we have done. So you can see earlier we have tried to keep the material volume constant. So now if we try to use a different constraint, so here we are trying to see what is the lateral surface profile of a bottle we can have if we try to have volume constraint. So let us say the bottle is having 1 liter of volume. Then what can be the surface profile which can actually give you maximum buckling load? So in this problem we have taken these parameters. So base radius is this, cap radius is this. So this is your cap radius and this is your base radius, and then volume is kept at constant, then thickness is given here, then material properties, boundary conditions, and the load is outside uniform pressure, so it is subjected to pressure load outside. And then if we try to set it in the optimization process and try to see what is the maximum or what is the like kind of shape which can give you maximum buckling load. So here, this is, let us say, the base model. So we have started with this and we have got buckling factor is 0.035. So let us say this is some factor. Buckling factor is kind of, you have a factor which has to be multiplied with the applied load to get the critical buckling load. Okay, when buckling factor is less than 1, that means you're like when we have tried to kind of in your analysis setup, you are actually giving a very high load. Okay, so if you it's kind of a linear relation for eigenvalue buckling analysis. It is linear. So if you increase the applied load, then BF will reduce, and if you reduce the applied load, then this buckling factor will, because the multiplication of these two will be giving you the ultimate buckling load. Okay, so we should not worry about whether it is less or 1, because that depends on what you have applied. So and we are keeping the same pressure, so then that applied load is same. So buckling factor, if it is like increasing, that means that candidate design is actually good. Okay, so here you can see in this candidate design you have a substantial increase from this 0.035 to 0.241. And this shape also is giving like substantial increase. And here we have got two shapes because in this particular optimization study, we are using F-min search, and F-min search actually is kind of a gradient-based optimization scheme. So it starts with your initial guess and depends the output actually. If there are actually local minimum, then probably you will end up with a local minimum depending on your the starting value or the initial value. So the point is here you can see the shapes are very interesting for this study. So NC and vessel, if you see, they have this amphora kind of shape. And this preliminary study, what we did earlier, so that actually was giving some similar shape. So maybe this can give some idea why in the ancient vessel they probably used to use this kind of shapes. Okay, so that has higher buckling strength than the normal kind of, or if you choose some arbitrary shape. So with this, the conclusions we have, like in this study, what we have done is when there are there are some geometry and loading involved where analytical solutions are not possible, then we can go with finite element based optimization study, and we can see that this kind of like optimization study can actually in principle give significant increase in the failure strength, keeping the material cost same. And then we can use like different constraint to eliminate also undesirable design. And if we have some manufacturing constraint, then that can also be implemented. We have to see what are those constraints, and then we can set up this problem according to that. Okay, so with this, I'll just end here. So if you have any questions, I'll be happy to address them.
So questions? No? Well, I mean, it seems we don't have many structures people in the crowd.
Yeah, maybe.
Okay, so thanks, Professor Jana, for giving this talk and
Thank you.
helping us understand some aspects of optimization in structures.
Yeah.
Well, then let's end this. Participants, we will meet again at 5 p.m. in the evening. And okay, have a nice day, all of you.
Yeah, thank you, Professor Akshit Prakash. Yeah, so we'll leave now.